Hi there! Welcome to this demo on Amazon S3, AWS Glue, QuickSight, and Athena. This project was created to help systems designers, data architects, and data engineers understand these services and their use cases for ad hoc querying and visualization. It's a fun project that uses a script called PyDragons. PyDragons is a Python script that's fully configurable. It generates two CSVs, one of dragon IDs and unique parameters of those dragons, and another of dragon actions. Those actions are things like looting, eating, burning, and sleeping. First, let's take a look at how our data is stored in S3. Right now, it's organized into raw data, transform data, and Athena results. We already have set up a dragon events table. You can see that here, under a database called PyDragons. We're going to do the same thing in this demo and create one for dragons so that those two tables can be joined and insights discovered about them. You'll see in Glue, we have our dragon events table here. The first thing we need to do is set up a crawler for our raw data in S3. Our raw data for dragons is stored under year, month, and day. This is important because it will help us with partitioning later. To set up a crawler, we click Add Crawler. We're going to use an existing data store and go down into our data stored in S3. We're not going to add another data store. We do, however, need to create a Glue service role. It's going to be run on demand. We already have a PyDragons database created, but if you need to create your own database, you would just click Add Database. We can update the configurations if we want for when we add more data, and then we're going to hit Finish. Once we finish creating the crawler, we need to run it. This may take a few minutes. Once the crawler has finished, you'll want to check your tables list. We see that dragons has been added. We're going to click it to check the schema. This looks good. There are some things that we would like to change. Event timestamp, for example, is being read as a string. Also, our partitions don't have labels. We can fix the partitions quite easily, naming them year, month, day, and save. We're going to transform this data, so we can change that string in another step, and we're also going to compress it. First, we want to check our data with a query in Athena. I have one written out here. You can see that the largest size dragon types are golden dragons. This data took 3.73 seconds to run, and it scanned 5.8 megabytes of data. Let's see if we compress to Parquet, if we can make that faster or have less data scanned. In Glue, we'll need to set up a job and create another crawler to post to our processed data table. I've already set up a Glue job role just for this reason. We're going to use the dragons table. We are going to change the schema, but we're going to create it in a new data target. We're going to change it to Parquet, and we're going to have that data go into our transform dragons folder. Here, we can change that string to a timestamp. Check everything else to make sure it looks good to go. Once we save the job, we can also edit the script for the job to add our partitions. We can then run the job. Now that our job has succeeded, we need to check to make sure the data was successfully converted to Parquet. And we can do that by going to our transformed folder, which we selected. I can see that the partitions are here and that the data is here as well. We still need to create a crawler so that we can crawl this data and put it in our PyDragon's process table, where we still don't have a processed, compressed version of the Dragons table. Since you already know how to create a crawler, I'm going to go ahead and create that in Glue so that it will show up in Athena, and we can compare the process data against the raw data. Okay, our crawler has now successfully crawled the data, and we can see that here in Glue. Our partitions are automatically included as well, and when we swap over to Athena, we also see that our table has now shown up in Athena. We can test our previous query, which scanned 5.83 megabytes of data, in this new processed data table. Parquet is more efficient to query. Athena costs $5 per terabyte of data scanned. As you can see here, this query scanned 1.44 megabytes of data, compared with our raw data, which scanned 5.83 megabytes of data. Now that we have our table set up in Athena and our data successfully compressed to Parquet, we want to move on to QuickSight. In QuickSight, you can see here that I have a series of visualizations set up for joining the two tables on the Dragon ID and analyzing that combined data. We have information about what our most dangerous dragons are based on how much damage they did. You can see that the golden dragon is the most dangerous, what dragons ate overall, and even all the way down to figuring out what individual dragon types ate. So it's a pretty interesting data set that you can discover and use QuickSight in order to create that information. I want to show you how to bring that data into QuickSight. When you first visit QuickSight, you'll have to create an account. I've already done that, but it's a very straightforward process. Once you've created an account, you need to create a new data set. You can see here that QuickSight allows you to create data sets from multiple sources, including CSVs directly, but we're going to use our Athena tables. Keep the work group. And this is in our PyDragon's process database. We're going to start with just the dragons table. And I would recommend using Spice. It's very fast. So when your data is imported, you can actually create these visualizations with rapid speed. Now that our data has been successfully imported, we can see that because we get a count of the number of rows. And I know that that's correct. First, we want to kind of investigate our dragons. For example, do we know what different dragon types there are? We can see that in two ways. We can create a pie chart if we want. So I've selected pie chart, and we can add type here to the dimension. You'll see there was an even number of dragon types in this set. It's not exactly equal, but it's very, very close. Since we know this data isn't super interesting, maybe our dragons are different sizes. So maybe we want to group this data in a different way. For example, let's add size feet as a value with which we're measuring those dragons. Now we're getting somewhere interesting. It looks like the largest dragons are probably golden dragons, but this is basing it on sum, which is summing up all the values for that particular column. Instead, we'd probably want to go use something like average or max or medium for this. This will give us a sense of the average size of a golden dragon. While this looks very much the same because the way the data is spawned is using a range and for each dragon type, we can now see that the average size golden dragon is 300 feet long. You can see the average size bronze dragon is only 50 feet long. So we know our golden dragons are really big, and our smallest dragons are purple dragons. I want to swap back over to our analysis that's joined on Dragon ID for the two tables, Dragon Events and Dragons. As you can see, this is the initial set of data. And from this, the Golden Dragons did $136 billion worth of total damage in that very small time frame. Let's imagine for a second that we felt like this was too high and it didn't really make sense within the world that we had. Or let's imagine also that these are players and that we were making some changes in either our game or our system that affected our players, resulting in a new set of data. And we wanted to compare this data with the data we have now. I did this by altering some of the reference material that's used for the Python script, that's also included with the Python script, so that our dragons were a little less dramatic. As you can see right now, our golden dragons are just way different than the rest of the dragons in the set. Their average damage done is almost 13 million damage. And that may make sense, except it may not make sense for them to do it within a 3-hour window. So instead, we may want to change those values. And as you can see here, I've now filtered it on the 21st, and it's really changed. Our dragon types are a little more closer together in the amount of damage that they do, but they're still different enough to where it's interesting. So this is the power of QuickSight for use cases not just in systems design, but A/B testing, and using filtering to actually compare and contrast your data across timeframes. Thank you for joining me in this demo. On S3 for your data lake, AWS Glue for ETL and compression, Athena for ad hoc querying, and QuickSight for visualization. I'll include relevant links to the GitHub repository in the comments. Feel free to look through the Python script, CSV, and truly make it your own.